The examples we've seen so far have been fairly mathematical, but some of the most interesting examples involving recursion are actually visual. And so let's take a look at how we would generate the graph paper you see here in a recursive kind of way. So how do we view this recursively? Well, what we're going to do is view the graph paper as being 4 graph paper pieces put together. So I can take my larger graph paper problem and say, well, that's really 4 smaller problems. If only I could draw a graph paper in each of the 4 smaller problems and they matched each other correctly at the edges, the result would be a piece of graph paper that looked like the original image. So for the example, we're going to represent the area we want to make a graph paper out of as having a lower left-hand corner, denoted xy, and a size, it's going to be square, so the width and the height are going to be exactly the same. So this represents the area in which we want to draw a graph paper, and the 4 subquadrants are shown here as well. Now it'll be helpful to label some of these points. So the point along the left edge that's halfway up is exactly the lower left-hand corner, but with the y-coordinate increased by size over 2. So size plus y would be all the way to the top of the square. Y plus size over 2 is halfway up, and so the point x, y plus size over 2, is a label coordinate for the middle of the left side. Similarly, the right side is exactly the same distance up. It's also y plus size over 2, but it's all the way across the square, so I have to take x and add size to it to get that far over. The bottom point, the midpoint of the bottom edge, is the same y-coordinate as the lower left-hand corner. It's exactly that high up, but it's x plus size over 2 across. So we want to take the lower left-hand corner x and creep over halfway across. That would be size over 2 added to that. And then the top is the same displacement horizontally, so x plus size over 2, but it's all the way to the top, so it's y plus size. So it's easy, relatively easy with some thought, to compute these coordinates, and having computed them, we can now think about the 4 recursive subcases, and we'll look at each one in turn. So let's look at the upper left-hand quadrant. So what is its lower left-hand corner? We already computed that. It's x and y plus size over 2. But we can think of it as having its own lower left-hand corner. The same thing with the upper right. The same thing with the lower left. Now its lower left corner is coincident with the larger square's lower left-hand corner. And then finally the bottom right. And so what we need to do for each of these subquadrants is to express them in terms of the larger problem. That involves labeling them consistently, namely finding their lower left-hand corner, which we actually already computed, and also how big they are. What is their size? So let's look at the upper left-hand quadrant first. Its lower left-hand corner is the middle of the left edge. We already computed that coordinate as x, y plus size over 2. And how big is it? Well, it's half the size across, and half as high also, as the original square. So we think of it recursively as having the lower left-hand corner specified there, but with half the size of the larger quadrant. Now the upper right one is halfway over and halfway up, so its lower left-hand corner are x and y with size over 2 added to each one of them. And its size is also size over 2. All these subquadrants are size over 2 compared to the larger square. The lower left one, as mentioned before, is coincident with the larger square, so its lower left-hand corner is simply x and y, and it's half the size as the larger square. And finally, the lower right one is x plus size over 2 over, and the same y-coordinate. We've seen this coordinate before as the middle of the bottom edge, and its size is size over 2. You're going to end up implementing this code to see how it actually works, but in terms of the recursive thought, this is the structure you need in order to be able to solve this problem recursively.